On this video we want to show frequency synchronization with the two different transmitter. A couple is analogic transmitter in the series EXC30GT, and another couple is digital DDS polyhedra transmitters. This is our base time, a GPS managed 10 MHz time base. The upper couple is two EXC30GT transmitters. One is on, the other is off. Let's turn the second transmitter on. Frequency is 99 MHz, 990 kHz. In this moment we have 15 Hz difference from zero. Difference is going to zero. 6 Hz, 5 Hz, 6 Hz. Let's increase the resolution of the frequency meter. Now we are 2 Hz and half. We need near 1 minute to have a difference less than 1 Hz. 0.7 Hz. .2 Hz. Now we go to compare the difference of the two transmitters on an oscilloscope. You see that the frequencies are equal, but there is some noise, some jitter, which is in the order of some hertz. This is unavoidable with analog synchronization. If we hear to the result on the modulator, we can hear the noise. We can also measure the sum of this signal on a modulation analyzer. This is the sum of the two synchronized transmitters. You see that the noise goes from nearly 70 up to 80 dB, so very good quality. If we hear that on a demodulated spectrum analyzer, we see that there is no noise. This equipment is used to receive and demodulate the signal. At this moment there is no signal. Let's connect. Well, no noise. Per favore, mi accendi? Now we are modulating with a pure tone 1 kHz. As you hear, there is no distortion. No noise if we remove modulation. This is the result on the spectrum analyzer. You see that the two transmitters sums and differs randomly, but there is no impact on the modulation. It's something like multipath. This is a spectrum analysis with fixed frequency, zero frequency, 1 second sweep. You can see the difference, which are in the order of 0 up to 10 Hz. Here we are again on the oscilloscope. We input two signals onto different axes, and we see the Lissajous figure. You see the noise. We are now looking at the digital couple. They are both at 98 MHz. They are emitting power just now, and this is the frequency. You see 97 MHz, 998 kHz, 674 Hz, i.e. it is 1.4 kHz lower than correct frequency. Now we put external time bias on. The frequenciometer gate is a few seconds. Frequency is just correct now. There is less than 0.1 Hz difference. Let's go to the oscilloscope. This is the oscilloscope screen with the Lissajous figure. You see that it is perfectly stable. Those are two inputs. You see that carriers are perfectly synchronized. Now we take one time base off. You see they are no more synchronized. Put the synchronization on, please. It's immediate. Now we use another external time base. Up to now we used the same output from the HP GPS managed time base. Now we use another time base, which is this one. You see they are still synchronized. Take time base off, please. Take it on. So no problem with the two different external time bases. There is still some frequency difference, but it is less than 1/30th of hertz. I mean, less than one cycle on 30 seconds. Okay. Let's see again on the spectrum analyzer. Here is the composition of the two frequencies. You see that the spectrum is very stable. In this moment is not modulated. Let's go to zero span. You see that is quite flat figure. If you compare this with the previous one, it's very different. Here we are again on the oscilloscope. This is unmodulated carrier. And this is modulated carrier by 1 kHz tone. You see some small error, but carriers are anyway synchronized.